Okay, so this is a work example, problem with a mass and the resistance. So please pause the video and read the text of the problem, and then we will solve it together. Okay, now if you have read the text of the problem, you know what you need to do, and here is our strategy. First, we're going to figure out the time of flight, and or rather, first we're going to figure out the range so we can figure out the time of flight. And once we have the time of flight, we have expressions from what we did in class for the x and y components of the velocity. So we can calculate those velocities as a function of time. We know now the final time of flight. We calculate the final velocities. So all sounds pretty straightforward, except that the equation may be a little difficult. The first thing we are going to use is the equation we derived in class for the range, and the equation, I'll remind you, read something like this: v was 0 plus v terminal divided by v x 0 times r, where r is the range, the unknown, plus v terminal plus tau times the log of 1 minus r over vx0 tau equals 0. And again, we need to solve this equation for r. So a bunch of things that need to be defined. We are aware of what all of these values are, or these expressions are, from various parts of our physics learning, some of them from the class on this topic, some of them we know from elsewhere. Vx0 is going to be v0 cosine theta, since we're given v0 and theta, not vx0 and vy0. And vy0 similarly is v0 times the sine of theta. We have an expression for tau. I'm going to write it next to this. Tau is m divided by the coefficient b, while v terminal is equal to m mass times g acceleration divided by b. Then we also, so let me start putting some numbers here. Call this equation 1. This will call 2a and 2b, 3 and 4. And we have an equation for the time of flight as a function of r. E is going to be equal to minus tau times the log 1 minus x divided by vx0 times tau. Where x is the input, the variable. So once I say how far has my mass gone in the x direction, I can calculate how long it took the mass to get there. Let's call this equation 5. And Vx is given by Vx0 e to the minus t over tau a, and Vy is given by, write in different ways, minus v terminal plus Vy0 plus V terminal e to the minus t over tau. Okay, and we'll just have to be careful about the sign. One is solved equation one numerically, or two was the approximate solution that we discussed in class to calculate an approximate value for R without solving a difficult equation. The way we do it is the following. Again, this to solve equation one, that in writing. We calculate R0, which is 2Vx0 Vy0 divided by G. And then go and calculate R1, which is going to be equal to R0 minus 2 divided, well, let me make this nicer, three Vx0 and then I have well, just tau. M would be, maybe it's too long. Okay. About that. And of course, as you remember from class, what I have is a second degree equation in R, so I could just solve that explicitly. But that's not really all that useful. As long as I can get some value for R, even if it's approximate. So now we pretty much have everything. We got R. Everything in this equation is known. We know Vx0 because we know V0 and theta. We know tau because that's going to be given in the input of our problem. So since we know R, we can calculate T. And once we know T, we can replace the value of T in equations 2. No, sorry, equation 6 for the velocities. And once we have the equations for the velocity, we can calculate the kinetic energy. Which is just going to be given by 1/2 of m times v squared, or the final over t initial is going to be equal to v final squared divided by v naught squared, since the masses are going to be the same. Okay, sorry. Now I'm going to make a let's set the mass just 1 kilogram. phi, I'm going to give a random value, sorry, theta, I'm going to give a random value of pi over 5. B is going to be 0.01, so relatively small value. For G, I'm just going to use 9.8. And for V0, I'm going to use 100. Just because it's going to make the math a little easier. But if I do that, I find that R0 is about 970.47, and R1 is 892.86. And I did this aside numerically, and I found that the correct value of R is 897.95. So you see that we're making a very small error with this approximation. And then we're asked to figure out the velocity when the object gets to the bottom. So I just replace, as I said, in equation 5 to find the time. From here to an arrow, I find that t is equal to 11.77 seconds. And once I know the time, I can calculate Vx and Vy. Vx final is equal to 71.92. And Vy final is equal to minus 56.5. So I can put those two together right here. The total velocity is 91.47. That compares to 100. So we've lost about 9%, 8.5% of our velocity. And if you square that, you get the loss in kinetic energy, which is going to be 0.8. Sorry, I'm looking for the number. Okay, here it is. I found it. So from here, I guess I can do another arrow. T final over T initial, or T0, is approximately equal to 0.83. With this approximate solution would actually be with a more accurate calculation, 0.8367. So it's really not a bad approximation at all. And that is all that we were trying to do for this problem.